Hi all. Okay. Last week we already looked into OpenMP. We already covered 2 weeks, and also this week we will finish it. Basically, just another few slides to finish, which is first is last time we already looked into our OpenMP program. This one I already share with you, and also about the treats, and we did also learn under static, dynamic, and guided. So on this OpenMP, basically what you need to do, please try to do the exercise from the coding that I provided in the notes and also in the class that we shared last 2 week and last week. So about the guide dynamic, I think we already looked into it and also guided. On runtime, it is oftenly we use that we know runtime is to look into your delay scheduling decisions, which is anti-runtime. And if we like to see the impact of various scheduling strategies to select the best one, the scheduling can be set to a runtime. So what normally you need to do under runtime, the environment variables is on schedule. So this is the normal things that you're going to use, and the variables that you need to use if you want to use runtime, which is determine the scheduling class and also shrunk size. OMS also it is a short form of OpenMP schedule. Value can be changed at the runtime, the moment just before the program is executed. So this is the example, which is the CS7V OMP schedule, which is static one. And next is under synchronization across multiple for directive. So you can see that it is often it is desirable to have a sequence of 4 directive within a parallel construct. So normally you're going to see it is there are across multiple for synchronizations for your directive. So it is that to not execute an implicit barrier at the end of each of directive. So OpenMP provide a cluster, which is the example is no wait. So this one we already look into. If you look on the notes I provided, you look several things we have learned, including the no wait. So the example over here is which can be used with a directive to indicate that the thread can be proceed to the next statement without waiting. So this is for no wait condition only. So you can also have check the no wait users example. So next is I think until here for your notes under OpenMP. Now I'm going to discuss with you another chapter, which is under your performance analysis. So performance analysis performance analysis, what you need to see is under a parallel algorithm, which is there is a involved between two, which is estimations of parallel performance limit from the analysis of its execution time, and another one is predictions. So there is two under estimation and also predictions on how much improvement can be achieved by increasing the number of processors. So there is a performance issues. If you check here, performance issues, there is a speed up. So this is the equations you need to use for performance issues related to speed up. So you have a speed up, which is a sequential execution time over parallel execution time. Speed up is a ratio between sequential execution time and the parallel execution time. So you using these two information, which is sequential execution time, you can divide it with parallel execution time, then you will get the speed up time. For another one, on the performance, if let's say you want to check and to justify your performance of your system, there is another issue, which is under efficiency. So under efficiency of a parallel program is a measure of processor utilization. We can define specific we can define efficient to be speed up divided by the number of processors used. So you if you want to check your efficiency, normally for other system we can use it as a accuracy, something like that. So you need to use the sequential execution time over processor use. How much the processors that you use for your specific programming times your parallel execution time, how long your execution took off. So then you will get the value of your efficiency. So you need to memorize these equations for speed up and also efficiency, because it's very important look for your final exam also. It's not final exam, final assessment. But if you didn't know how to calculate the speed up and efficiency, you cannot check how much your performance is depending on the speed up and the efficiency. So performance analysis formula, 4 well-known performance predictions you can use to check your performance: Amdahl law, Gustafson-Persis law, the cut-flat metric, and the last one is the isoefficient metric. So there is 4 performance analysis formula that you can use to check your performance. You need to memorize and also understand all 4 performance analysis formula. So under Amdahl's law, you need to know that this is the Amdahl law, but under Amdahl law, what you need to check first is you're going to look into your speed up, of course. So this is the equation, but this equation only under M law, and there is also given the examples after this you're going to look into. And Amdahl law provide upper bound on the speed up achievable by applying a certain number of processors to solve the problem in parallel. So let's say F to be fractions of operation that must be performed sequentially, where 0 equal or more F, and then similar also you need to have F less or equal to 1. So you need to have more than 0 and less than 1. So in between, F is the number in between, or maybe also you can have 0 and also 1. The maximum speed up as achievable by a computer with P processor performing the computations is, so S equal to 1 over F plus 1 factorize 1 minus F then over the P which is the number of your processor. So given a sequence, let's say this is just example, you are given the scenario. So the scenario is when you are given the sequential program, which is the program called as A, and then you were given also the value for execution time, which is 16%, and also you need to know that this is execution time from the functions that could be performed in parallel. So you know that it's already get 60%, mean in decimal is 0.6. So how are you going to find your F? From here you know that F is your fractions. So your F is wait, I cannot move to the, okay. So F, you need to get 1 minus 0.6. This one is the equations for speed up. So that's why you need 1 minus F. F is your fractions time, which is 60% or equal to 0.6. That's why you will get 1 minus 0.6. So you get 0.4. For P, you continue read what is the maximum speed up. So you need to find the speed up. If it gives you another conditions, which is program is converted into a parallel program and execute in a computer with 8 processor. So you already know also that P refer to the processors number, how many processors there are used. So it's direct question. I think fractions, you can know that it is 0.6. In it is the numbers of processors over here. That's why you will put it into your equation. You will get 1 over 0.4 plus 0.6 over 8. This one is over 8. It's only for your fractions, equal to 2.1. So please try to do it and find whether you can get an answer or not, but it is simple and too direct. Now you look into your Gustafson basis law. So this is for you to estimate scale speed up rather than for, it's hard for me to move around. So rather than Amdahl law, you need to know that it is for you to find the maximum speed up, while for Gustafson basis, it is for you to estimate the scale speed up. Still under speed up, but it's quite different between the maximum and the scales. So estimate the scale speed up, which is how much faster the execution time of parallel computations of a multi-process computer than execution time of the same computations of a single processor computer. So the equation scale speed up, which is this one, you were given less or equal P, same the number of processor, plus factorize 1 minus P, which is number of your processor, and S you will get it from your previous law, which is called as Amdahl law. So S is fractions total execution time spent in serial code, but sometime in the, what is this, sometime if let's say in the question or situation you were given the values of S, you can use it directly. So over here there is an example. Let's say you have a program B, which is a parallel program, and you already given 10% of the execution time. So what is the meaning of 10%? Is 0.1 So you need to know it is 0.1 execution time. So you will directly given already of the execution fee and etc. I think it's too direct, also quite similar to previous example. I hope that you can try to apply into your Gustafson basis law. So we move to another law, which is under curve-flat metric. So this is useful to determine the factor of efficiency discrete problem of your parallel program. So this is the experimental determined serial fractions for E. So whereby P equal to numbers of processors similar as E, the experimental determined speed up. And then you can look also the values is constant for limited opportunities for parallelism and increase for parallel overhead, like example start delay, communication delay, and synchronizations. So this is the curve-flat metric example. You can see over here, if you have the P numbers of processor, what is the value of your SE? So from given example, can you get the serial fractions? Because serial fractions is depend on the SE, which is experimental determined speed up, and also numbers of processor. You just apply into this equation from the table given. You will then get the table for you to answer for each condition. If let's say processors is 2 and SE is 1.8, what you're going to get for your E. We call it E as a symbol. Where is it? Wait, I cannot move. Okay, this is E. I call it but basically it is a serial fractions, and you can try to apply it under your curve-flat metric tables give example, and you use the tables given to get the answer. Lastly, the equation under the isoefficient metric is used to determine the scalabilities of your parallel system. A parallel system is perfectly scalable if the same levels of efficiency can be sustained as a processor are added by increasing the size of the problem being solved. So this is under your efficiencies metric. So only these 4 equation you need to remember. Where is it? Okay, under your performance analysis. So upon on this, until the isoefficient metric, you already finished cover all. So I hope that you can try to check several tutorial or exercise under all these problem performance analysis, and try to apply on several scenario and get your answers. First of all, as I can say, that you need to know all the formulas, all the equations, and throughout it's quite easy for you to just apply it. So thank you for your watching for this video. Later on we will meet again in our next class, and we're going to discuss about our exercise, tutorials, lab, and etc. Thank you and have a good day. Bye.